All right, today we're going to look at 12.5, the effects of negative feedback on op-amp impedances. Now, we know we get an op-amp. That op-amp got certain characteristics. All right, now what's going to happen when we apply negative feedback? The overall characteristics of the complete circuit will change. Now, the first one, we're going to look at the input impedance of a non-inverting amplifier. And we will go and have a look what is going to happen to the input impedance of that circuit. Now, in the circuit, I can state that Vin is equal to Vd, my differential voltage, plus my feedback voltage. There's my input voltage, there's my differential voltage, and there's my feedback voltage. That means the input voltage will be the total of those two voltages added together. Here's my feedback circuit, Rf and Rin. I will have a certain amount of attenuation. The attenuation will be determined by Rin divided by Rin plus Rf. That is a normal voltage divider. Now, by substituting my attenuation times my output voltage, that will be equal to my feedback voltage. I repeat, the attenuation times the output voltage will be equal to my feedback voltage. I will substitute that into that equation. Then I will have Vin is equal to my differential voltage plus attenuation times my output voltage. All right, we know that the attenuation is equal to Rin divided by Rin plus Rf. And we also know that V out is approximately equal to the open loop gain times my differential voltage. And we know the open loop gain of an op-amp is very high. Then I can state Vin is equal to Vd, my differential voltage, plus my open loop gain times my attenuation times my differential voltage. I can take Vd out, my differential voltage, out of that equation, and that is going to be equal to 1 plus open loop gain times my attenuation times my differential voltage. Now my input current times my input impedance is equal to my differential voltage. That's Ohm's law. Current times resistance will give me voltage, all right? And then I can say Vin is equal to 1 plus open loop gain times my attenuation times In times Zin. That is basically substituted for my differential voltage. They say well, Zin is the open loop input impedance of the op-amp without feedback connections. That means that input impedance there is of my op-amp itself. That you will find, will get it from the data sheet. But Vin divided by In will give me my overall input impedance. That means of the complete circuit, and that is equal to 1 plus open loop gain times my attenuation times Zin. I repeat, that Zin is of the op-amp itself. Then I can say Vin divided by In is the overall input impedance of the closed loop non-inverting amplifier configuration. That's why I can say Zin of a non-inverting amplifier is equal to 1 plus open loop gain times my attenuation times Zin. Now we can see that my input impedance of the non-inverting amplifier is going to be much higher than the input impedance of the op-amp itself. That means the input impedance will increase a lot, will increase by this factor. Now we're going to look at the output impedance. What's going to happen to the output impedance of an op-amp? We know that the idle op-amp or an op-amp got a very low output impedance. But if we apply negative feedback, that output impedance is still going to decrease. It's going to make it smaller. And we want a quite small output impedance. That means the moment we're going to apply negative feedback on this non-inverting amplifier, the output impedance will also decrease. All right? We're again going to apply Kirchhoff's voltage law. By applying Kirchhoff's voltage law, we can state that V out is equal to the open loop gain times my differential voltage minus Z out times I out. You see, there is Z out. That is Z out is of the op-amp itself. That is internally in the op-amp, the output impedance of that op-amp. Then they state the differential voltage, Vd, is equal to Vin minus Vf. Therefore, by assuming that the open loop gain times my differential voltage is much larger than Z out I out, you can express the output voltage as V out is approximately equal to open loop gain times V in minus Vf. Now V in minus Vf will give me my differential voltage. Now again we substitute my attenuation times V out for Vf. Then I can say V out is approximately equal to open loop gain times V in minus my attenuation times V out. Expanding and factorizing the yields, we can say that V out is approximately equal to open loop gain times V in minus open loop gain times my attenuation times V out. That means we multiply just through this equation with my open loop gain. And then I can, by taking that equation to the other side, I can say V open loop gain times V in is approximately equal to V out plus my open loop gain times my attenuation times V out. We take V out as a common factor, then I can say it's equal to 1 plus the open loop gain times my attenuation times V out. They say since the output impedance of a non-inverting amplifier configuration, Z out of a non-inverting amplifier is V out divided by I out. Now that will give me my total output impedance of the circuit. And now I can substitute I out, Z out of a non-inverting amplifier for V out. Therefore I can say open loop gain times V in is equal to 1 plus the open loop gain times my attenuation times I out times Z out of a non-inverting amplifier. Now we want the output impedance of a non-inverting amplifier. All right, now we divide both sides of the previous expression by I out. Then I get the open loop gain times V in divided by I out is equal to 1 plus the open loop gain times my attenuation times Z out. The terminal left of the internal output impedance of the op-amp, Z out becomes, because without feedback, the open loop gain times V in is equal to V out. Therefore, we can state that Z out is equal to 1 plus the open loop gain times my attenuation times Z out of a non-inverting amplifier. Now this is the output impedance of the complete circuit. That output impedance is of the device itself. We want that is the unknown. Then I can say Z out of a non-inverting amplifier is equal to Z out divided by 1 plus open loop gain times my attenuation. Now this indicates quite nicely that my output impedance of a non-inverting amplifier is going to decrease a lot. It's going to decrease by this factor. Let's have a look at the equation of example 12.5. Let's quickly have a look at example 12.5. They state, example 12.5a, determine the input and output impedance of the amplifier in figure 12.24. The op-amp data sheets give Z in 2 meg ohm. You can see the input impedance is quite high, 2 meg ohm. The output impedance is also quite low, 75 ohms. Open loop gain is 200,000. But we know for a 741 op-amp that we're going to use in the practical work, the open loop gain of a 741 is in the region of 200,000. All right. Now we can have a look. The circuit shows us that is a non-inverting amplifier. It's a non-inverting amplifier. RF is 220 kilo ohms. Rin is 10 kilo ohms. I work out my attenuation. It's Rin divided by Rin plus Rf, and that will give me 0,0435. Now my input impedance is going to increase by this factor. That's why it's going to be 1 plus 200,000 times my attenuation times my input impedance, all right? And when we work that out, it will give me a total input impedance of 17,4 giga ohm. Now you can see the input impedance of the device was 2 meg ohms. Now it increased to 17,4 gigaohm. This is a large number, and the practical purpose is we can assume infinite as an ideal case. We're going to assume basically infinite input impedance. That means we're not going to draw any current at the input of that device. All right. The output impedance was given as 75 ohms. Now that is also going to decrease by this factor, 1 plus open loop gain times my attenuation. That means 75 ohms going to divide it by that, and that will give me 8,6 milliohms. Now you can see the output impedance was 75 ohms. It decreased to 8,6 milliohms. The closed loop gain of the amplifier is now going to be 1 plus RF over Rin. 220K divided by 10K, and that will give me a closed loop gain of 23. The device gain, open loop gain, was 200,000. Because I apply negative feedback, the gain decreased to 23. All right, that means now it will give me much better linear operation in this case. All right, we can also look at voltage follower impedances, and we know in the case of the voltage follower, our attenuation is 1. That means in the case of the voltage follower, we will have the highest possible input impedance, because then it's only going to be 1 plus my open loop gain times the input impedance of the device itself. That means very high input impedance. The output impedance will be the output impedance of the device divided by 1 plus the open loop gain. You can see a very low output impedance. Let's have a look at the example 12.6. They say the op-amp in example 12.5 is used the voltage follower configuration, determine the input and output impedances. The same device, the voltage gain, open loop voltage gain was 200,000. The input impedance was 2 meg ohms. Now when we work that out, we get an input impedance of the voltage follower of 400 gigaohm. The output impedance of the device was 75 ohms. And when we divide by this factor, we will have an output impedance of 375 micro ohm. Now we're going to look at the impedance of an inverting amplifier. Now in the case of the inverting amplifier, we go a little bit backwards. We know the op-amp always try to make the input impedance or make the input voltage difference equal to 0. That means here at my non-inverting input, that is at 0 volts. Now the op-amp will adjust its output in such a way, if it's not saturated, to take that also to 0 volts. That means this input voltage is equal to 0. That means my input impedance in the case of this device will be determined by Rin. Actually Rin in parallel with the input impedance of the device. But this is normally very high, let's say 2 meg. You've got a 10K here. That means the input impedance will be approximately equal to Rin. Right, here they tell us input impedance, Zin of an inverting amplifier is approximately equal to Rin. There they show us, there is virtual ground, it's not connected to ground, but it is exactly the same potential as ground, and there is my input resistance. Alright, the output impedance of that will be exactly the same as for the non-inverting amplifier, and that's going to be Z out over 1 plus the open loop gain times my attenuation. Let's have a look at the example. Example 12.7, they say find the values of the input and output impedance in figure 12.27. Also determine the closed loop voltage gain. The op-amp has the following parameters: open loop gain 500,000, Z in 4 meg ohm, Z out 50 ohms. All right. My input impedance you don't even have to calculate, is equal to Rin. Zin of inverting amplifier is approximately equal to Rin, it's equal to 1 kilo ohm. That is my input resistance. My attenuation is equal to Rin divided by Rin plus Rf, and that will give me 0.001. Then the output impedance of the inverting amplifier is Z out, that was given, of 50 ohms, divided by 1 plus open loop gain times my attenuation. And when I work that out, it will give me 980 milliohms. The closed loop gain of the inverting amplifier is equal to Rf over Rin. Rf is 100K, divided by Rin is a 1K, and that will give me minus 100. The minus sign only indicates that we got a 180 degrees phase shift between my input and my output. I repeat, the minus sign indicates 180 degrees between the input and the output, because if I apply a positive voltage in, I will get negative voltage out. If I apply negative voltage in, I will get positive voltage out. All right, now we're going to do 12.6, bias current and offset voltage. Certain deviations from the idle op-amp must be recognized because of the effects of its operation. Transistors within the op-amp must be biased so they have the correct values. The bias and collector currents and collector to emitter voltages. The idle op-amp has no input current as at its terminals, but in fact, in practical op-amp has a small input bias current, typically in the nanoamp range. Also, small internal imbalances in the transistors effectively produce a small offset voltage between the inputs. These non-ideal parameters were described in section 12.2. Now we know the input stage of an op-amp is a differential amplifier, and our transistors are not identical, and we need to bias a transistor to switch it. Now we're going to look at the effects of input bias current. All right, if we look at the inverting amplifier in this case, in the case of the inverting amplifier, there is a small bias current flowing, and due to the bias current that flows, if we look at the input voltage is 0, that means my output voltage should be 0, but due to this input bias current that's flowing through RF, I will have a small output that's equal to I1 times RF. That current that's flow times that, it will be positive there, it will be negative there because the current's flowing in that direction. We make use of conventional current flow. In the case of the voltage follower, here we got the voltage follower. That means we know the attenuation is basically 1. And what actually will happen if I apply 0 volts, I should have also 0 volts out. But due to the bias current that's flowing, it will create a volt drop and it will give me a certain output voltage. In the case of the non-inverting amplifier, again, 0 volts in, I should get 0 volts out. But there is again a bias current flowing, this I1, and that will give me a certain output voltage equal to I1 times RF. All right, what we're going to do, I'm going to quickly repeat the bias current compensation for op-amp configurations. First of all, we're going to look at the non-inverting amplifier. In the case of the non-inverting amplifier, I will have a look at Rin and Rf. I will get the effective parallel resistance of those two, and that will be equal to my compensating resistor. That's RC stands for compensating resistor, is equal to Rin in parallel with Rf. And I will insert it there. Normally, there won't be a resistor there. In the case of the inverting amplifier, again, I will do exactly the same. RC will be Rin in parallel with Rf, and I will insert it there to compensate in the case of my inverting amplifier. All right, what we can do to eliminate the need for bias current compensation, we can make use of a BiFET on the input stage of the op-amp. And we know a JFET got a very high input impedance, and that means if we use a op-amp with a bi-FET input stage, then we don't need to do bias current compensations. All right, effects of input offset voltage. In the case of the input offset voltage, we can also apply a voltage there in the case of the voltage follower, and that will also make sure that my output error voltage is also going to be equal to 0. Oh, I must move, sorry. All right, there we can see we apply that voltage there on the input of the voltage follower to make the offset voltage equal to 0. Input offset voltage compensation. In the case of the 741 op-amp, we also got the facility built into this device where we can use pin 1 and pin 5, and they call that my offset null, and we just take a potentiometer from my negative supply voltage and we can adjust it to make it 0. That means that is internally built into this op-amp device. All right, we can do that by putting that 10K potentiometer there to the negative supply and adjust it if my input is 0 to make sure my output is also 0. .7 open loop response. Now we're going to look at the frequency response of an op-amp. We're going to look at the open loop response of the op-amp. You also had a look at frequency response in chapter 10. That was done in electronics 2. Now again, we're going to look at frequency response, and we're going to look at open loop, and we're going to look at closed loop. Now if I look at the op-amp and I look at the open loop, in the case of open loop, I don't have any feedback. You can see there's no feedback from the output to my inverting input. Then I can say that my open loop gain is V out over V in, and we know the open loop gain of a 741 is in the region of 200,000. That means we got a very high open loop gain. Other op-amps got much higher open loop gains than 200,000. Now when I apply negative feedback, here's the inverting amplifier, I apply negative feedback. With the negative feedback, my closed loop gain is equal to minus RF over R in. The minus sign just indicates again 180 degrees phase shift between my input and my output. All right, here they talk about bandwidth limitations. Now we're going to look at the bandwidth or the open loop frequency response, or they talk about the ideal plot of an open loop voltage gain versus frequency of a typical op-amp. The frequency scale is logarithmic. That means this scale here is logarithmic. All right, first of all, they show us 106 dB. My open loop gain is 106 dB. Now if we go and look at 106 dB, it will be equal to 200,000, all right? And my critical frequency is equal to 10 hertz, all right? And then you see as the frequency increase, I will start getting a decrease in my gain. Higher frequency, lower gain. The roll-off is equal to minus 20 dBs per decade is the roll-off. In this case, that means the frequency increase, my gain will decrease. 0 dBs is equal to 1. That's why they talk about unity gain frequency, because 0 dBs is equal to 1. 106 dB is equal to 200,000, and that is the open loop frequency response of op-amp. All right, in this case, that is basically of a 741 op-amp. Things you should know, critical frequency, and we know that an op-amp can also amplify DC because it's directly coupled. That means it can amplify DC as well as AC. All right. Here they talk about the 3 dB open loop bandwidth. All right. Bandwidth, if you remember from chapter 10, bandwidth is the upper critical frequency minus the lower critical frequency. But now, because this thing can amplify DC, the bandwidth is only going to be equal to the upper critical frequency because the lower critical frequency is equal to 0 hertz. They say now from now we can refer to FCU only equal to FC because that is my upper critical frequency. All right, unity gain bandwidth. All right, there they talk about the unity gain bandwidth. I've told you 0 dB is equal to 1. There they show us 0 decibels equal to 1. And that's where we get our unity gain bandwidth. Now gain versus frequency. Here we got a RC lag circuit. In the case of a RC lag circuit, there's a resistor capacitor. We got this at the output stage of the op-amps, and that's a RC lag circuit. And we know, as the frequency increase, what happened to my capacitive reactance? My capacitive reactance decrease as the frequency increase. That means, as the frequency increase, this AC resistance or capacitive reactance will decrease and my output will decrease. Now there's my input and there's my output. Now they say V out over V in. V out is across XC, all right? V in is basically those two together, R and C. That means I can say the square root of R squared plus XC squared. All right, now they say dividing both the numerator and denominator on the right equal to the sign by XC. Then again we can say V out over V in is equal to 1 divided by square root 1 plus R squared divided by XC squared. The critical frequency of an RC circuit. This formula you're going to use a lot. Go and know it because the critical frequency is 1 upon 2 pi RC. We're going to use this in filter circuits. We're going to use this formula a lot. Now divide both sides by F. Then we can say FC divided by F is 1 upon 2 pi RC times F, and that is equal to 1 upon 2 pi F times C times R. They say since XC, my capacitive reactance, is 1 upon 2 pi FC, the expression can be written as FC divided by F is equal to XC divided by R. Substituting the result of the previous equation for V out over V in produce the following expression for the attenuation of a RC lag circuit in terms of the frequency. V out over V in is equal to 1 upon the square root of 1 plus F squared divided by FC squared. That will give me my attenuation of my lead lag circuit. Then we can have a look. Here they show us an op-amp represented by the op-amp represented by the gain element of an internal RC circuit. You can see here's my op-amp and here is my RC lag circuit. Then I can say my open loop gain is my open loop mid-range gain divided by 1 plus F divided by FC squared. Now this F is the actual frequency at which the op-amp is operating. Now you can see what's going to happen to my open loop gain. My open loop gain will decrease as the frequency increases. All right, just to show that again, we look at this frequency response here. You can see as my frequency increase, what happened to my gain? My open loop gain decreases. That means higher frequency, lower open loop gain. And that's the formula we can use to determine that. There we got open loop gain is open loop mid-range divided by 1 plus F squared divided by FC squared. Let's have a look at example 12.8. They say, determine the open loop gain for the following values of F. Assume FC open loop is equal to 100 Hz and the open loop mid-range gain is 100,000. Now they start with 0 Hz, 10 Hz, 100 and 1,000 Hz. Now if I got 0 Hz, there's not going to be any attenuation. That means my open loop gain is still going to stay 100,000. Then we go to 10 Hz, then it decreased to 99,503. Then I go to 100 Hz, then it decreased to 70,710. And then when you go to 1,000 Hz, it decreased to 9,950. You can see what happens as the frequency increases, my open loop gain decreases. All right, again, we're going to have a phase shift. If we're going to look at my RC lag circuit, I will have a phase shift. Theta is equal to minus arctan R divided by XC. Or I can say theta is equal to minus arctan F divided by FC. All right, here they show us. Here we got a lag circuit. There's my input sine wave. And there I got my output sine wave. And you can see what happens. It lags the input. All right. That's what will happen in an RC lag circuit. That means with a circuit like this, the maximum phase shift I can create is 90. And the minimum phase shift is basically 0. And that brings us, they show us it approaches minus 90. That means it's a lag circuit. Now let's have a look at this example to illustrate the following. They state, calculate the phase shift of the RC lag circuit for each of the following frequencies and then plot the curve of the phase shift versus the frequency. Assume FC, the critical frequency, is equal to 100 Hz. And then we start with 1, 10, 100, 1,000, 10,000. If I look at the first one, if I use 1 Hz, I will have a phase shift of minus 0.573 degrees. Then we go to 10 Hz, then it's minus 5.71. Then I go to 100 Hz, then it's minus 45 degrees. Then I go to 1,000 Hz, then it's minus 84.3 degrees. Then I go to 10,000 Hz, then it's equal to minus 89.4. Now you can see the lower the frequency, the less the phase shift. As the frequency increases, my phase shift will approach 90 degrees. 89.4 degrees, it will approach 90 degrees as my frequency increases. Right, now we're going to look at the overall frequency response of an op-amp. Now, in an op-amp device, if you buy an op-amp, there's not going to be only one op-amp in that package. There can be more than one op-amp in that IC package. Each one with its RC lag circuit. In this example, we got 3 internal stages in the op-amp. We got AV1, there's AV1's response in the red. Then we got AV2's response in the green. And then we got AV3 response in the blue. All right, that is my 3 op-amps. That's the individual responses. All right. Now, if we're going to look at the composite response, if my gains was given in dBs, the overall gain will be all the gains added together. That means if they give you the gains in decibels, the overall gain will be the total of them. AV1 plus AV2 plus AV3 will give me the overall gain. The first one will give me a roll-off of minus 20 dBs per decade. The second one will give me minus 40. And the third one will give me minus 60. And here's the critical frequency of the first one, the critical frequency of the second one, and the critical frequency of the third one. And then they give us our overall phase shift, theta total, minus arctan F divided by FC1, minus arctan F divided by FC2, and minus arctan F divided by FC3. That's for the overall phase shift. To illustrate that, we're going to look at example 12.10. They say a certain op-amp has 3 internal amplifier stages with the following gains and critical frequencies. Stage 1, AV1 is 40 dBs, critical frequency 1 is 2 kilohertz. Stage 2, AV2 is 32 decibels, critical frequency is equal to 40 kilohertz. Stage 3, AV3 is 20 decibels, and critical frequency 3 is 150 kilohertz, all right? If I want to determine the overall mid-range gain, it's going to be all 3 added together, 40 plus 32 plus 20, and that will give me 92 decibels. I agree, I re-emphasize, if you got your gains in decibels, you just add them together. And then the total phase shift, if I work each one out, it will give me a total phase shift of minus 48.6 degrees.